We said, by the way, that when you create an abstract class, you must specify that the abstract class's destructor is virtual. Actually, that applies here to the employee class as well, because in this case, for our employee manager CEO hierarchy, the employee class is the basemost class, and if we need to have destructors for employees, managers, and CEOs, and we need to be able to allocate and deallocate these things on the heap on the fly, the employee class's destructor had better be virtual, so that when we dynamically allocate a CEO and later deallocate the CEO, the destructor for the CEO will be called first, followed by the destructor for the inner manager part, followed by the destructor for the inner employee. It's reasonable to ask, well, why aren't destructors virtual all the time? And the reason is that using virtual functions, which implies setting up this vtable in memory and having to indirect on functions through that vtable, takes a little more time than just having functions that are hardwired. And one of Strustrup's design principles for the C++ language was that you never have to pay an efficiency cost for any feature that you don't plan to use. So if you want to use virtualness, you have to ask for it. If you don't ask for it, you don't get it. All right, so let's use what we've learned about class hierarchies, abstract classes, virtual functions, and virtual destructors by taking a look at the creation and evaluation of arithmetic expressions. Now here, thanks to the PowerPoint Apply to All facility for the footers, I've got my name as the copyright holder of all of this stuff, but in fact I stole this from Professor Stephen Rarig, so his name really should be there. My apologies to Steve. So an arithmetic expression consists of a collection of terms. Term is an abstract idea. Some of those terms are constants, like 5 or 17. A constant is a kind of term. Some of the terms are binary operators, like plus, minus, times, divide. Binary operator is also an abstract class. It is a kind of term, and then we have specific binary operators. Plus is a kind of binary operator. Minus is a kind of binary op. Divides is a kind of binary op, and so on. Here on slide 25, we have a diagram of this class hierarchy. Term is the base class of everything. Kinds of terms include expressions, variables, and constants. Okay, so we've talked about a constant like 5 or 19 as being a kind of term. A variable, which you will deal with in the homework, is also a kind of term. And also, an expression is a kind of term. Now, an expression is composed of a sequence of terms hooked together by binary operators like plus or minus, or perhaps preceded with a unary operator like plus or minus. So, in the diagram with these blue-green circles on the right, we have an expression tree representing the arithmetic expression 1.1 plus 2.2, that quantity plus 3.3. We want our code to be able to store these expressions and to be able to display the expressions in a human-readable form, and also to be able to compute the value of an expression. So let's take a look at the code for this, starting on slide 26. All right, we include headers that we're going to use. One of these headers, which is new here, is the S-stream header. Previously, we've used the F-stream header, which allows us to either read from or write to files on disk. So if you create an OF stream object, that's an output file that you can insert text into using the insert or put to operators. Whereas if you create an ifstream object, that creates an input file that you can extract or use getLine to read information from an input file. sstream here is going to enable us to insert characters into a string object or to read characters from a string object. That is, we can treat a stirstream object as though it were an output file or an input file. Okay, so our basemost class is term. And term is very simple. Term has a constructor that doesn't do anything. It also has a virtual destructor that doesn't do anything, but it's very important for that virtual destructor to exist, since we're using term as an abstract base class for all of the various specific kinds of things that are going to make up our expressions. The two functions that we're going to need to have overridden at each higher level in this class hierarchy are called toString, which is going to take the current term and convert it to a human readable string, and toValue, which is going to take the current term and produce a double value of that term. Now, term itself, of course, is abstract, so we're establishing toString and toValue as pure virtual functions in the term base class. Now let's look at constant. On slide 27, a constant is a kind of term. It has a private data member called value containing a double, and notice that its constructor simply assigns the argument value provided to that value data member. The destructor is virtual, and the destructor does nothing. Now, since we've declared the base class destructor to be virtual, it's actually optional to declare this derived class destructor as virtual, but it's fine. And since we're not allocating or deallocating any memory here, it's not necessary for this destructor to actually do anything. Next we have the toString and toValue member functions for this concrete class. Constant is a concrete class. We can actually have constants, whereas term is an abstract class. We can't actually have term objects in our code directly. We can't say term t in our main function, but we can say constant c parentheses 7 to create a constant object named c containing a 7. Okay, so toString and toValue have to actually do something in the case of a constant. Let's look at toValue first. toValue is very simple because all it needs to do is to return the value of the value private data member. ToString is a little bit messier. We're creating an OStringStream object named OSS. That data type is described in the sstream header that we showed over near the top of slide 26 over here. And what's nice about the OStringStream class is that we can treat it like a file, and we can simply insert the value of this data member named value into OSS. And then to obtain a string object from OSS, we can use the member function stir. Okay? So we create an empty OStringStream object named OSS. We insert value into OSS, which will take that double value and convert it into a sequence of characters. And we can then obtain that sequence of characters as a string object by saying OSS.stir. And we are returning that string as the value of this function. Okay, so that's all we need for the constant class.